This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today. Two terms that are involved in bond parameters that we have discussed already. Okay, so one is bond length, another one is bond order. So bond order and bond length. Let me show all the bond parameters that we have seen in the last class. Okay, so these are all the bond parameters: bond length, bond order, bond enthalpy, bond angle, resonance, and polarity of bonds. And out of this, we have covered two. That is the first two, bond length and bond order. So now we will start the next one, which is bond enthalpy. Okay, so bond enthalpy, which is basically, it will be number 3. Okay, it will be number 3, not 4. And after bond enthalpy, there will be discussion related to bond angle, resonance, and polarity, if time permits, polarity of bonds. So bond enthalpy, what is the definition of it? It can be defined as the energy required to break all covalent bonds of a specific type. That means you cannot consider just any bonds. It must be a bond of specific type. By specific type, I am trying to say, suppose carbon hydrogen bond or oxygen hydrogen bond, like this. You cannot consider one CH bond or one EH bond. No, that is not correct. You have to consider just any a particular type of bond in 1 mole of a chemical compound, and it must be in gaseous state. So all these factors you have to keep in mind when we are defining it. Now it is a measure of strength of chemical bond. That means if bond enthalpy is very high, that means strength of this chemical bond, that will also be very high. Okay. So now we will see that what is the difference between bond energy and bond dissociation energy, because sometimes these two terms are so close we can consider as if they are same, but actually there is a difference. Okay, so when we are saying bond enthalpy or bond energy, whatever you say, because both are having same energy unit, but we are trying to see here the difference with bond dissociation energy. So when there is this term bond dissociation energy, not bond energy, so these two are not same. Okay, so the latter, that is, latter means the second one, the bond dissociation energy, that is actually the change in energy which is associated with homolytic cleavage of a bond. Homolytic cleavage means, suppose you have bond between A and B atom. Now if I am saying it is homolytic cleavage, that means when this bond will be broken, there will be one A atom and one B atom. And you can consider as if it is A dot and B dot. A dot means A carrying single electron, because in this bond we have a pair of electrons. So one A atom with one electron, one B atom with one electron. Okay, so this is homolytic cleavage. Similar type of cleavage. It is not ionic cleavage, that there is a positive charge over A. After AB bond breakage, there is positive charge over one atom, negative charge over one atom. No, it is not like that. It is homolytic cleavage. So the latter is the change in energy associated with homolytic cleavage of a bond. But the former means this one, bond energy. This is a former. The former is basically the average of the bond dissociation energy of all the bonds. But remember, in the bracket what is mentioned of specific type. So here we will see one example, then you will be able to understand what is the difference between these two terms. One is bond energy, another one is bond dissociation energy. Okay. Here we have taken water molecule, very common. So in case of polyatomic molecules, that is where several atoms are present, two or more same bond types. So here when you are considering water molecule, here we have basically hydrogen, then oxygen, then another hydrogen atom. That means how many OH bond present? Total 2 OH bonds are present. Okay, so when we are considering 2 OH bond and Then if you consider homolytic cleavage, so H2O molecule in gaseous state we have taken 1 mole. Gaseous state 1 mole H2O we have taken. Now after homolytic cleavage, so suppose one of these bond is broken. Let me use another color. So suppose this bond is broken. Okay, so there will be one hydrogen atom and one OH. So there should be actually a single electron, that is a lone electron should be there, but electron is not mentioned here. Just consider as if it is one hydrogen atom, one OH. Okay, if you are specific, you can put a dot sign, which is basically the sign of single electron. But whatever it is, you have to remember it is not H plus or HO minus. It is homolytic cleavage. So it is H gaseous state, HO gaseous state. And when the first bond is broken, the corresponding enthalpy change, it is denoted by del H1 and the value is 502 kilojoule per mole. So this is the energy unit. Now the OH fragment that is present, in this OH, if you are further breaking the second HO bond, now what will happen? You can see now you will be getting the second bond dissociation enthalpy, which is del H2, and the value is not same. It is 427. It is slightly lesser than the previous value. So it is not necessary that both the HO bonds should be having same value of bond dissociation energy. Okay. So these two values are individually bond dissociation energy, not bond energy or bond enthalpy. It is bond dissociation energy. And when you are taking the average value of these two, that is you are taking the summation of 502 and 427 and then you are dividing it by 2. Then the value that you are getting, see what value we are getting here, 464.5 kilojoule per mole. So this is the value of bond enthalpy. Okay, so I hope now it is clear what is the difference between bond enthalpy and bond dissociation energy. Fine. Now there are some factors on which these bond enthalpy values dependent. So here you can see the factors. The first one is atomic size, then electronegativity value of the two atoms for which you are considering the bond enthalpy, then extent of overlapping, because if extent of overlapping is very high for these two atoms, you know, we have seen that when bond formation is taking place, there is overlap of atomic orbitals. So if this overlapping of atomic orbitals for these two individual atoms, if this is high, obviously bond enthalpy, that is to break the bond, obviously you have to provide more energy. Okay, and the last point is bond order. So bond order we have seen in the last video is very simple, basically the number of bonds that is present between two atoms. So if I am saying what is the bond order for CC double bond, the answer is simple, it is 2. What is the bond order for CC triple bond? The answer is 3. So when bond order is very high, obviously bond enthalpy will also be very high, because to break 3 bonds, obviously it requires more energy compared to breaking 1 bond, right? So that is why all these 4 points you have to keep in mind, because they directly affects bond enthalpy. Okay. Next one is number 4. It is bond angle. Fine. So we are now discussing the 4th parameter of bond parameters. There are several parameters. So now we have reached number 4. The first 3 we have covered. It is bond length number 1, bond order number 2, and number 3 bond enthalpy. Now we have reached number 4, which is bond angle. We know that covalent bonds are directional in nature. Okay, and directional nature means there will be some specific orientation in 3 dimensions. So there will be specific direction in space. Now because of this specific direction of these bonds, obviously because of this directional nature, basically there will be a fixed angle present between 2 covalent bonds. Okay, and these 2 covalent bonds that originate from the same atom in a molecule, and this angle is termed as bond angle. Now same atom originate from same atom, what it means? When we'll see the example, it will be clear. So here you can see some pictures. The first one is linear shape For example, you can consider carbon dioxide molecule because this is linear, or you can consider BeF2, that is also linear. The central atom is carbon and both sides, so these two as if oxygen. I am here just giving the example of CO2. You can also consider any other linear shape molecule. But the important point is here this OCO angle, that is 180 degree. Then the next one, here we have trigonal planar. The central atom is this one, which is slightly larger in size, and the three surrounding it, they are slightly, it is shown in slightly smaller size. For example, if you consider this one, BF3. So here central atom is boron, and we have three fluorine atoms surrounding it. And this is a planar molecule, but important point that we have to consider here, this BFF angle. So you can write it as if, sorry, it is ABF angle, not BFF. So ABF angle, this angle is 120 degree. Next we have tetrahedral. Very common example is, you can consider methane. Now when it is tetrahedral, that is the shape of this molecule is tetrahedral, the HCH angle, this angle is 109 degree. Next we have the shape trigonal bipyramidal. A very good example is, this is the central atom. Suppose the central atom is phosphorus, and then all these positions. So here two types of angle you can see, right? So these two positions, suppose there is, if you consider P, okay, let me write PCl3, that is very good example of trigonal bipyramidal. So all these are chlorine, and you can see, unlike the previous examples, here we have two types of angle, right? So the first angle you can see 120 degrees. So as if you are joining all these three atoms, so in this case you can join all these three chlorine atoms, you will see, will get a triangle type of shape. Okay, and this ClPCl, this is as if vertically passing through this trigonal shape region. So this is the trigonal shape, and if you focus on this trigonal face, these angles, that is chlorine phosphorus chlorine angle, these angles are basically 120 degree. But if you consider this chlorine phosphorus chlorine angle, this is again 180 degree, and here it is written 90 degree because it is showing this particular angle, which is obviously 90 degree. That is this chlorine phosphorus chlorine, this angle is 90 degree. Okay, so in this particular shape you can find two different angles. These two angles are already mentioned. If you are considering this vertically oriented these three atoms, then the angle will be 180 degree. So it depends which atoms you are considering. And the last one, here we have central position, there is atom, and you can see if you join all these four atoms, you will get as if a square. Okay, and if you are having these vertically oriented atoms, now the angle will be, so this angle if you consider, this is actually 180 degree because you can see it is vertically oriented. But what about this angle? This angle is 90 degree. Okay, what about this angle? This is also 90 degree. What about this one? This is also 90 degree, and this one, this is also 90 degree. Okay, and let me show after erasing it. If you consider this angle, then this is again 90 degree. Okay, so this type of shape is octahedral. Now after seeing all these examples, one thing is clear, that the shape is directly related to angle, or you can say depending on angle we will have different types of shape. So it means now we can make this, we can state that the shape of the molecule that controls bond angles. So what type of shape the molecule is having, depending on that angle will be changing. and hence bond angle provides insight into the molecular geometry of the compound. So if you know the angle, obviously you can have some idea about the geometry of these molecules. Now some specific examples, if we see, the first one is methane, CH4. Okay, so here you can find similarity with this structure, methane. I have already shown it. Then we have ammonia. Now ammonia, there are total 3 in each bond. Okay, now this is also tetrahedral, but we do not have 4 hydrogen, unlike methane where you have total 4 carbon hydrogen bond, but now you have only 3 nitrogen hydrogen bonds. Okay, so the fourth position there is basically lone pair present. Now the angle is just like tetrahedral, but because of this presence of lone pair, you can see the angle is slightly deviated from the ideal angle of tetrahedral geometry. The ideal angle is basically 109 or 0.5, more or less same. But when there is a lone pair, because of repulsion between lone pair and bond pair, what I'm trying to say by repulsion, in any bond there is a pair of electron, and this is lone pair, this is bond pair, right? Now there is repulsion between this lone pair and bond pair. So because of this repulsion, now this angle, it will be shrinked slightly. But you can also say that there is also repulsion present in case of CH4, that is repulsion between 2 bond pair, right? Then why we are not considering? But remember, repulsion between bond pair and bond pair, that is one type of repulsion, and repulsion between bond pair and lone pair, these two are not similar type. So bond pair repulsion is lesser than bond pair lone pair. Okay, bond pair lone pair repulsion is always high, so that is why the angle is shrinked slightly from 109, now it is 107. Now this type of repulsion effect between LP and BP, that is lone pair and bond pair, further you can see that in water molecule. So in water molecule HOH, there is 2 oxygen hydrogen bond, but there is also presence of lone pair. So just compare with CH4. CH4 is tetrahedral, ammonia is tetrahedral, this is also tetrahedral, but now we have only 2 bonds, and rest of the 2 positions of tetrahedral geometry, there will be presence of lone pair. Now the number of lone pair compared to ammonia obviously increased, and that is the reason now LPBP repulsion, that will also be very high. Now look at the angle, it is further deviated. So if you compare with 109, it is, the gap is around 5 degree, but when it is ammonia there is only 1 lone pair and the gap is 109 minus 107, around 2 degree. Okay, so in this way it is because of presence of increase in the number of lone pair, there is increase in LPBP repulsion, and that is the reason bond angle is shrinked. Okay, so that is all about bond angle. The next parameter is resonance. Now this is very important, not just in chemical bonding chapter, because this unit is all about chemical bonding. Resonance you will also find in organic chemistry or any, that is other chapter also. That is, this is, if you have clear idea about resonance, you can apply that idea in several places. It is a very you should all have proper idea about resonance. It is very, very important. Okay, so what is resonance? Lewis structure, how to draw that we have already seen in the first part of this unit, right? Now there are many occasions that may arise where you will see that more than one Lewis structure you can draw for a particular species. Okay, that means all are valid, so you cannot cancel any Lewis structure. So now when all are valid, all these structures, they are related to each other as resonance structure. So suppose for a particular species you are having total 3 resonance structure 1, resonance structure 2, resonance structure 3. So all these resonance structure, they will have some contribution to the actual structure, and this type of resonance structure you will see for some species, they are equivalent. When I'm saying equivalent, that means when you will draw the structure, suppose 3 resonance structures are there or 2 resonance structures are there. So when you will draw the structure, you will not find any difference between them. They are all equivalent to each other, but that may not be always. So when it is not happening, it will be non-equivalent resonance structure. A single Lewis structure is not enough for the representation of a molecule. Now, when we are saying this, what we are actually trying to say. So suppose for a particular molecule, you are having some experimental result. That is experimentally determined parameter. Suppose you have measured bond angle for a particular molecule. But when you are considering a single Lewis structure, it is not matching with the experimental result. That is, from the single structure, the bond length that you are expecting, you are not getting that in the experiment. But when you are considering the other structure, that is, you are considering the contribution of both the structure, or I can say you are considering the average contribution for these 2 structure or 3 structure, then you will see it is matching with the experimental observation. So that means just to have so that the theoretical result it is correlating with the experimental result. So if we are considering the average Lewis structure, then only we can find this type of correlation. So that is why we should consider the resonance structure. We should not be considering only a particular structure, especially in these cases where experimental result is completely different. Okay, so see this example. Ozone. We know this molecule O3, 3 oxygen atoms are present. Now here you can see these 2 structure. Suppose this is structure 1, this is structure 2. Now you can see both these structure. If I am not marking the oxygen atoms, both these structures are basically same. So it is basically equivalent resonance structure. Now when I'm saying same, that is without numbering, they are actually same. And that is very clear to understand, because in this molecule there is one oxygen-oxygen double bond and one single bond. And that is true both for structure 1 as well as structure 2. But suppose I am numbering it. So the left hand side oxygen is 1, this is 2, this is 3. Left hand side oxygen 1, this is 2, this is 3. So in the first structure you have 1, 2, these 2 oxygen are having double bond, and 2, 3 single bond. But in the second one, that is not the case. So when I'm numbering, then you can understand that they are not equivalent. But without numbering, they are actually equivalent. But the important point to notice here, if you simply consider a particular structure, then you should have 2 different types of bond length, because you have one double bond, oxygen-oxygen double bond, and you have one oxygen-oxygen single bond. And we know that single bonds are longer. So you should have 2 different values of bond length. One is 121 picometer, another one is 140. But experimental result is saying something completely different. It is saying that it has only one value. That means you have to consider the average of these 2 structures. Now when it is average of these 2 structures, now it will be looking like this. See, this is the average structure. So now there is a dotted line. It is not that any specific double bond you cannot see, any specific single you cannot see. So as if when we draw average structure, we use this type of dot. So as if the double bond is spreaded all over the molecule. And that is the reason now when we have written this charge, in both structure, the middle oxygen is fully positive charge. So it is +1, that is fine. But if you consider the 2 terminal oxygen 1 and 3, in the first structure, number 1 oxygen is neutral, number 3 is negatively charged, and in 2 it is the reverse. So when you will consider average, now both are as if having minus up. And look at the average value. This is the experimental value for oxygen-oxygen bond length in ozone molecule. So if you simply consider a particular structure 1 and 2, it is not matching with the experimental result. Okay, so now we can say that the accurate representation of the molecule that is ozone molecule, is given by this resonance hybrid. Hybrid means it is a combination of structure 1 and structure 2. Okay. So remember this resonance hybrid in bracket what is mentioned, it is not a conventional Lewis structure. We do not draw this type of Lewis structure. When we have learned how to draw it, we have not seen this type of thing. But now as we are now learning resonance, so you have to now understand how to draw this average structure, because that is, if you consider this, then only you can explain the experimental result. If you are simply considering these two individual structure, it is not matching with experimental result. Fine. So it is clear. Next thing that you have to understand, here two things are written. In the right hand side picture, minor contributor is mentioned. In the left hand side picture, major contributors mentioned. So what it means actually? See, major contributor means in this resonance structure, we have a double bond and we have single bond. But when it is minor contributor, basically these two structures are also, I'm numbering it, suppose it is 3. Now 3 and 4, if you compare with these two, they are also equivalent individually. I am not saying they are equivalent to 1 and 2, but 3 and 4 equivalent one side, 1 and 2 equivalent other side, and 1 and 2 together, because these two are equivalent, they are major contributor. Then 3 and 4, these two are also same equivalent, but they are minor contributor. Now both these resonance structure, you cannot say that they are not valid. They are actually valid. You can draw them. And how we are getting these 3 and 4? Just see, consider structure number 1. So considering structure number 1, if I am breaking this CC double bond and I am putting this negative charge over the middle oxygen, now this terminal oxygen, it will be positive charge, positively charged, and the middle oxygen now will be neutral. So in this way, from structure 1, you can get structure 3. Similarly, in the structure 2, if I am breaking this bond between 2 and 3 and putting the electron density over oxygen 2, now O3 will become, number 3 oxygen will become positive. See, this is positive. I am not considering this one. I am just focusing on 2-3 bond. So I am just breaking one bond. Middle oxygen is now neutral, that you can see in structure 4. But number 3 oxygen is now becoming positive. But why we are saying that this is minor contributor, though this resonance structure is possible? So next thing that we have to learn is, though all these structures you can draw and you can say all are resonance structures, but which resonance structure will be contributing more to the actual resonance hybrid? How to decide that? That rules we have to learn. Okay, it is not that all the resonance structures are equally valid. Here total 4 structure you can draw, but out of these 4, 1 and 2, which are equivalent to each other, we are giving more significance to this, because these resonance structures are having more stability compared to these minor contributors. But how to understand that? For which we have to know the rules to decide which resonance structure will be having more contribution. But before that, some more discussion we will see here. It is found that the energy of the resonance hybrid, you have already seen the resonance hybrid of ozone, and the energy of this hybrid, it is lower than that of all possible canonical structure. That is another name of resonance. It is same thing. And that is why we consider the resonance hybrid, because we always try to accept that structure which is having lowest energy. So this structure, as it is accepted, it is matching with the experimental result. The energy of this hybrid is lower than any other possible structures. And the difference in energy between the most stable canonical structure and the resonance hybrid. So suppose there are total 4 resonance structure, 4 canonical structure. Okay, and out of these 4, there is one structure which is most stable. So I am just writing it. Don't just consider the previous example. In general, suppose there are total 4 resonance structure. Okay, let me write 3 resonance structure. And out of these 3, suppose this is the most stable. and you have resonance hybrid. Now the difference between the energy, difference between the most stable structure and the hybrid, that is called resonance energy. Resonance forms that are equivalent, you have already seen there is no difference in stability, so their contribution is equal, and that we have already seen that when you consider the average of ozone molecule, just remember the previous example, when you take the average of structure 1 and 2, their contribution is basically equal because they are equivalent, so obviously their contribution will be equal, but that may not be always. So the first example you are seeing here, this is basically equivalent structure. So which molecule it is? It is polyatomic ion CO3 to negative charge. So this is structure number 1. This is structure number 2. This is 3. Now all these 3 are basically equivalent, right? Unless you put some numbers, it seems equivalent. But if you really want to see the difference, just put number over this oxygen, don't need to put number over carbon. So in the first structure there is double bond between carbon and oxygen number 2. In the second case there is double bond between carbon and oxygen 3. In the last structure, double bond between carbon and oxygen number 1. Now these 3 structures 1, 2, 3 all will have same contribution, okay, because they are equivalent, so that is why their contribution will be same. And now look at this resonance hybrid structure. Overall charge now it is written within third bracket outside, and dotted lines are used. And now you cannot say that any particular oxygen will be having full negative charge. Now this total negative charge, which is basically 2 minus, that will be distributed over 3 oxygen. So individually you can put minus 2 by 3 over all these oxygen. Just you have seen in case of ozone, we have written minus half over these 2 terminal oxygen. Same thing you can also do it here. Now it will be total 2 negative charge. It will be distributed equally over 3 oxygen, so it is be minus 2 by 3 each. But what about non-equivalent structure? So when there is non-equivalent resonance structure, the bonding and charge distributions are not same. So they are in different energy level. So suppose there are total 3 resonance structures. All these 3 are not equivalent. They are different. Now, one thing I would like to mention, in the previous slide, though we have total 4 structures, but 1 and 2, they are equivalent to each other. Similarly, 3 and 4, they are equivalent to each other. But if you compare 3 and 4 together with 1 and 2, now you cannot say they are equivalent. So 3 and 4 are not equivalent to 1 and 2. So when you have to decide whether to consider 1-2 pair or 3-4 pair, then you have to apply the rules that we are now going to see. Similarly, in this slide, you can see this example OCN. So in the first structure, there is negative sign over oxygen. In the middle structure, there is no negative sign, as if this negative charge over oxygen, there is negative over nitrogen. If you are making OC double bond by using this negative charge, now there is double bond between O and C, but there will be negative charge over nitrogen. Okay. So here the formal charges are basically mentioned. And in the last structure, how to get the last structure? Let me write it. The last structure you can get from 2. If oxygen is using another lone pair, so now there will be triple bond between O and C, and the carbon nitrogen bond will be broken. There will be another negative charge over nitrogen. So total 2 negative charge. But the important point is you can clearly understand 1, 2, and 3 for OCN minus. OCN minus, you can write it like this, as if one single negative charge. So for non-negative resonance structure, some are more stable, some are less stable. So how to decide which structure? As you can see here, for OCN you have 3 types of structure. So how to know which structure you should give more priority, or you can say which structure will be having maximum contribution to the hybrid. Okay, so to decide that, next we have to learn some rules for finding the most stable resonance structure. So here 5-6 points you will see, and obviously when you will apply the rules, you have to maintain this order, because there will be total 5 to 6 rules, and maybe in some molecule you are getting 2 rules, that is it is in one structure. Suppose first, according to the first rule, the first resonance structure is predominating, but according to the last rule, second structure is predominating. Now the question arises, which rule you should give more priority? Obviously, that is the reason you have to maintain this order. So the first rule, you will see it will have maximum importance. So what are the rules? Let's see one by one. The structure with more number of covalent bonds, that is more stable. So in some structure, you can consider the previous one. Though in previous case, that rule is not applicable, because in all these structures, 1, 2 or 3, there are total 4 bonds, whether that is between oxygen, carbon, carbon, nitrogen, whatever it is, but total number of bonds 4, right? But in some resonance structure, you will see this is not different. Then you can apply this rule. You have to choose that structure where covalent bonds maximum. So the structure with more number of covalent bonds, that is more stable. So look at this molecule. This is, organic molecule, acetone, CH3COCH3. Now there is double bond between carbon and oxygen. Now if you break the pi bond, there will be negative charge over oxygen. We are putting negative charge over oxygen because that is preferred. Oxygen is more electronegative, so better you put negative charge over oxygen. But the important point is, here you have total 3 covalent bonds, 1, 2, 3, but in the previous case you have total 4 bonds. So that is why this structure is better, more contributing. Next point, the structure with more atoms having complete octet is more stable. Now this 1 and 2, these two rules are not actually separate, though we have written it separately, but you will see when maximum covalent bonds are present, mostly those molecules you will find where all the atoms, their octet is complete. Just take this example that we have just seen here. From the point of view of second point, from the point of view of first point, why the first structure is better, that logic we have already seen. But what about octet? Now, if you consider the second structure, surrounding carbon, there are total 3 bonds. That means surrounding carbon, there will be total how many electron? 1, 2, 3, 4, 5, 6. So total 6 electrons surrounding carbon. That means carbocation, it is actually carbocation, positive charge over carbon. Octet is not complete. But if you consider other atoms, if you consider oxygen, there are total 3 lone pairs and 2 electron available. So total 8 electrons surrounding oxygen. And for all this carbon also, as there is tetravalency maintained. So 8 electrons are present. So in this structure, except the carbocation, all are having octet complete. But if you consider the first structure, you will see octet is complete for all the atoms, though it is not applicable for hydrogen. So just forget it. Forget, because for hydrogen we do not use the term octet. Octet is not applicable here, it is duplet. But without oxygen, if you focus on this carbon having 4 bonds, so total surrounding carbon total 8 electrons. So octet is complete. So from the point of view of second rule also, the first structure better. Okay, so these two rules, they go together. Next, another example you can see, CH3, then N triple bond N. Now the middle nitrogen, as it has total 4 bonds, it is positively charged. If you are breaking one of the bonds between, that is any of the bond between nitrogen, middle nitrogen, now it will be neutral, but the terminal of nitrogen, that will be positively charged. Now these examples also, you can consider it from the point of view of rule 1 and rule 2. If you consider rule 1, the first structure having 4 bonds, so it will be better. If you consider from the point of view of octet complete or not, then also you will see in the first structure octet is complete. whether it is carbon, nitrogen, or this nitrogen. But for the second structure, these two fine, but the terminal nitrogen in the right hand side, which is carrying the positive charge, total 8 electrons are not present because two bonds, that means 4 electrons, and these two, to total 6. So octet is not complete for this terminal right hand side nitrogen. Okay, so that is why the first structure is better. Now the first 2 points are most important. Whenever you will be getting different resonance structure and you have to check which one is having maximum stability, give importance to the first 2 rules. Come to the third rule, the structure with least charge is more stable. Now to give example, just take the first example, because second example you cannot consider. In the second example, in both the structure you have some positive charge. But if you consider the first structure, that is, I'm talking about acetone, here the first structure it is neutral, second structure you have some positive charge. So from the point of view of third rule also, the first structure is better because it is having no charge. So always consider that structure which is having least charge. Okay, but again I'm saying, if suppose rule 3 is maintained and you are choosing some structure, but that structure is not giving you complete octet. In this case, it is giving you complete, but not always necessary. Then don't go with the rule 3. Give more priority to 1 and 2. Okay. The structure with negative charge on more electronegative atom or positive charge on more electropositive atom, that is obviously stable. Because we always try to put negative charge over more electronegative atom. Suppose negative charge is present. Just take this example, acetone. So when you are, I should not consider this one because we have to take that type of example where in one resonance structure the negative charge is present on less electronegative and the other structure is present on more electronegative. Then which structure you should consider? So for that you have to consider this resonance. Here negative charge is present over carbon. But when this negative charge, it is just follow this arrow. There is formation of double bond between these two carbon. So this double bond is now broken. There will be negative charge over oxygen. So among these two structures, the second one is better because in the second structure, negative charge is present over oxygen. And we know in the first structure, it is over carbon. And oxygen is more electronegative than carbon. So obviously, the second structure is better. So for this fourth point, you can consider this structure. But remember one thing. In this example, there is no issue with octet. In both the structure, octet is fine. But suppose in one structure, there is negative charge over oxygen. Another structure, there is negative charge over not, there is positive charge over oxygen. But still, maybe even after having positive charge over oxygen, it is fulfilling the criteria of octet complete. Then obviously you should give priority to that. Though there is positive charge over oxygen, just ignore that. Give more priority to the fact that octet is complete. Okay. And the last point, the structure with least separation of opposite charge. Now this is not always applicable. Suppose in a structure, one structure, there is positive and negative charge, and that is separated by 3 atoms. So suppose there is 3, just I'm writing arbitrarily, there is positive, there is negative. Another structure, this positive and negative, it is present side by side. So when opposite charges are present, obviously if they are close to each other, that will be more stable. So that is, it is written here that the structure with least separation of opposite charge, that means they are very close to each other, that will be more stable. And the most important point, these rules you have to apply in the order mentioned. Keeping that in mind, the number 1, 2, 3, 4 are written. So 1 and 2, these are most important, and 1 and 2, you will see these two go with each other. When octet is complete, you will find more covalent bond in that structure. Okay, and vice versa. So these rules are to be applied in the order that is mentioned. Here we have a problem based on this, that is how to apply these rules. Arrange the following resonating structure according to their contribution towards resonance hybrid. So here we have the fragment CH2N2. See, there is one positive charge, one negative charge. So in general, you can write the molecule as if it is CH2N2. It is actually known as diazomethane, but if you write the structure fully, it will be like this. Okay. Now the first point, check in which structure maximum number of covalent bonds present, because that will also fulfill the octet criteria. Structure A, total 4 bonds, right? 3 bonds, 3 bonds, 4 bonds. So obviously A and D will be more stable than B and C. Now in which option you have A and D before C and B? It is only option A. So don't you think this is enough information to choose the correct option A? Okay, but we will also see why A is more stable than D or C is more stable than B. Individually also we have to check. But one point is clear, that A and D, these two together, A and D, this is obviously more stable than C and D. And that is because of this number of covalent bonds. You have to give priority. And with respect to charge, you cannot do anything because in all the structure you have positive and negative charge. Though their distance is, in some case it is close, in some case it is not close. And in structure A and D, you will also see this negative positive charge, they are close to each other. But you don't have to think so much. Just check the number of covalent bonds. That information is enough to be confirmed that A and D will be more stable than C and, sorry, it is B, not D. Now come to next point, why A is more stable. Now in A, here we have negative charge over nitrogen, but in D we have negative charge over carbon, and the middle nitrogen, it is always positive, both A and D. So obviously we have to give priority to A. So that is why A will be more stable than B. Then what about C and B? Now come to C and B, these two. In C and B also, if you look carefully, in structure C, negative charge is over nitrogen. In structure B, negative charge is over carbon, right? So that is why you have to give more importance to C. So C is more stable and A is more stable than D. So A, D, C and B. First option, fine. So this is the order of stability. Though in the question it is written a different way, it is asking according to their contribution towards resonance hybrid. But this is another way of saying stability order. Because when stability is high, contribution is also high. So if you are finding the order for contribution towards resonance, that is A is having maximum order, sorry, A is having maximum contribution, then the next species is D, which is having maximum contribution to hybrid. So it is same thing, whether you say it in terms of contribution towards resonance hybrid or you say the stability order, both are actually same thing. Okay, so option is the correct option. Which of the following resonating structure of 1-methoxy-1,3-butadiene? If you are, though here exact name, how this IUPAC name you have to draw the structure, that is not required, but still for if you are interested, I'm just showing here 1-methoxy-1,3-butadiene. So suppose the structure is not given and you have to draw the structure, then what you will do, 1,3-butadiene, that means total 4 carbon, but, and at 1 and 3 position, this is 1, this is 2, this is 3, this is 4. At 1 and 3 position, there will be double bond, and at 1 position there is methoxy group. So this is actually the molecule, though it is written in different ways, but actual molecule is this one. These are the different resonance structure. Now we have to find among these which one is least stable. That means you have to find the most unstable structure. So again, what we will do, we will try to see in which case there is maximum number of double bonds present, because that is the easiest thing you can do, right? So in the first structure, A structure, total number of bonds 7, right? Then in the next structure, 2, 1, 1. This is also 7. Then structure C, 6. This is also 6, right? So obviously A and B and C and D, the least stable structure will be in between us. The least stable structure will be any of the structure out of C and D. A and B cannot be correct option, right? Because there are maximum number of double bonds present. Though you can say that in structure A and B there is positive charge over oxygen and oxygen is electronegative. But remember, I have said, though there is positive charge, but if the criteria for octet is maintained, or the criteria for covalent bonds, maximum covalent bonds, that criteria is maintained, you don't have to think about whether positive charge is over electronegative present or not. Now this is in terms of covalent bond that you can easily count, but if you want to check whether octet is complete or not, that also you can do. See, when oxygen is positively charged, here lone pair is not written, but basically there is also lone pair. Oxygen, when it is simply having 2 bonds, there are 2 lone pair, but when there is positive charge, there will be 1 lone pair. Now count the total number of electrons surrounding oxygen. Total 3 bonds, that means 6 electrons, and there is non-bonding electron pair, so 8 electrons. So though it is positively charged, but it is having fully filled octet, so it is stable. Fine. So A and B cannot be correct option. Now come to C and D. How to choose between C and D? Which one is more unstable? Right? Now in structure C, there is 1 positive charge, 1 negative charge. In structure D also there is 1 positive charge, 1 negative. So you cannot do anything. There is a tie. Next point is, what is their distance? So in D structure, they are present side by side. Here also they are present side by side. Now how to decide? There is again tie. Now the interesting point. See, in case of D, this lone pair over oxygen, it can show Plasar effect. And when it will show Plasar effect, then the structure will be like this. Double bond oxygen, CH3. And this part there is no change. It is as it is. No change. So this type of resonance structure is possible. Okay. But if you say, why not resonance structure possible for C? Here also it is possible. Yes, it is possible. But it is not immediate neighbor. That means here the lone pair that can be donated, then it is stable. Let me draw the structure. H2C negative. Now it is having double bond, then CH, then O positive, double bond, CH2. Now this is also resonance here possible, but here it is immediate neighbor, but it is not immediate neighbor in option C. So that is why C will be more unstable. So the logic is, explanation is given here. See what is written. In structure D, A and B already cancelled because they are stable. Octet is complete. Among C and D, you have to now choose. What is the logic? In structure D, electron deficiency of positively charged carbon is compensated by 1 pair of electrons that is coming from neighbor oxygen, adjacent oxygen. But that type of neighboring group support is not available in C. It is not neighbor, it is coming, but far, it is coming from farther distance. So that is why you cannot say this is adjacent oxygen atom present. So that is the explanation why C is the least stable structure. Okay. Next we have the next parameter, which is polarity of bonds, though we will not be able to finish it, but just try to see some initial idea. Polarity of bonds, that means there will be some polarity generation in the bond. Here you can see 2 pictures. One is diatomic chlorine molecule, simply chlorine molecule. But if you write it, there is a single bond present between 2 chlorine. Both the atoms are same, right? Electronegativity same. That means the electron that is present in this bond, these 2 electrons, that will be equally shared by these 2 atoms because they're same atom. So this is purely non-polar covalent bond. But if you look at the second structure, this is hydrochloric acid. Now chlorine is much electronegative than hydrogen, right? So the electron density that is present, it will be closer towards chlorine. Okay, let me write it clearly. The electrons that are present, it will be close to chlorine, not hydrogen. So that is why now it is written here, electrons shared unequally. So though it is covalent bond, and what we know, the definition of covalent bond, it is equally sharing of electrons between the two atoms. But what is the nature of the atoms? Depending on that, slight amount of polarity may be generated or may not be generated. In case of first molecule chlorine, there is no polarity generated because both sides are symmetrical. But in the second case, chlorine will be attracting the electron density. So though it is covalent bond, but still you can say that this is polar covalent bond. But this one is non-polar covalent bond. Try to understand the difference. Okay. So existence of a 100% ionic bond or 100% covalent bond, that is actually the ideal situation. So if you have any covalent bond, there may be, depending on the molecule, there may be some polarity, slight polarity. Or if you have any ionic bond, then also there may be some covalent nature. So in purely ionic bond, you can have some covalent bond nature and vice versa. So in this case, we are trying to see in covalent bond how ionic, not exactly ionic, better I say in covalent bond, how polarity can be generated. Next, there is another topic will be there where we will try to see in pure ionic bond how covalent character generated. That we will see later. But right now what we are seeing in covalent bond how polarity can be generated, and that you can see from these two examples. So remember, in ideally it is we give definition of ionic bond covalent bond, but in reality no bond or a compound you can say that it is completely covalent or ionic. Only in this some rare cases you can see where both the atoms are same, you can say it is purely covalent. It is completely matching with the definition of covalent bond. But ideal cases mostly you will not find. So more we'll see on this, but we are at the end of the session. Thank you for listening.